Well, we consider a particular model of directed random graph. That is the construction of the model. It has 5 basic parameters: alpha, beta, gamma, delta, 2 values of delta, and it has it starts with some given graph, fixed, with a fixed number of edges, and it has time. Time starts with t0, that is the number of edges in the start graph, and it makes several steps. Every step is first selects a random arrow in this picture. There are 3 processes. The first, with probability alpha, one adds a new edge and a new vertex to some existing vertices in the graph. With probability beta, we add a new edge between 2 existing vertices, and with probability gamma, we create a new edge from some existing vertex to a new vertex. 2 existing vertices are selected with the probability depending on their out degree for sources of the edge and in degrees for target of the new edge. This model was presented in by these authors in 8 years ago. So we analyze some statistics in this model. Some basic facts. Number of edges is equal to the time, because at every step we always add a new edge. A new vertex is created with some probability from 0 to 1. We assume that this probability is non-zero. Otherwise, the model is not interesting. And the total number of vertices is highly concentrated around some constant multiplied by number of edges. The first problem is description of in degree or out degree sequence. Obviously, out degree is symmetrical to in degree with some parameters exchanged, so it's sufficient to study in degree sequence. There are some special cases. If one of parameters is 1, then every new vertex becomes has the in degree 1. And if another special case, if gamma is equal to 0 and preferential attachment never selects a 0 degree vertex, then every new vertex continues to be to have 0 in degree. The authors of the article that I stated below consider the cases when the degree is fixed and number of edges grows, and they prove the power law for these parameters. The power law has the exponent of power law is shown, is calculated with from model parameters. The remainder term is O small is not is good when d is fixed, but when d starts to grow, that is not very good bound. Another result, another known result was proved by Cooper. For he considered some slightly more general model, but and attains these results. Essentially, power law with until degree reaches some power of number of edges. And the remainder term is, it decays when it grows, but decays quite slow. Our results. The theorem that we prove says that the expectation of a number of vertices with given degree is in fact main term, the remainder term is in fact bounded uniformly on the degree. And this is true for any degree, not only bounded by some power of t, but of course when d grows, this decays from some constant multiplied by t to O at 1. It's interesting to note that O at 1 it is actually the exact bound in something special case. What if gamma and delta is A0, then even it is possible that there are vertices of the maximal possible degree if the initial graph is a star, then all new edges are directed to the center of the star. So when it is a special case, but when parameters are close to this case, then we must then it is true that this quantity can decrease very slowly. So what one is quite exact bound. What about concentration? I do not have yet a rigorous theorem, but I have some preliminary calculations that show that in fact there is a tight concentration until O at 1 is reached. So if this quantity still grows, if the degree and number of edges are related so that this grows, it is more than O at 1, then there is high concentration. The proof of both these statements use recurrent equations. The model is defined in terms of several steps, so it is natural to analyze the effect of every step. In every step, we have three possible processes. For new in, this process adds one new vertex with in degree 0, and it increments in degree of some vertex selected according to the preferential attachment. Thus, we can calculate the conditional expectation given that we know graph on some step, and we know that this process is used. We have, if d is 0, we get one new vertex in this quantity. We have a number of vertices from the previous step, and with that probability we lose one vertex. With that probability we gain a new vertex. Two other cases are similar with a special value for d 1 in u out, and no special values for old process. And so this yields a recurrent equation. And now we want to take an expectation, a global expectation. Unfortunately, n is it is concentrated but the variations can be quite large, too large for our results. So we take an expectation over all graphs with fixed number of vertices, and that if n is fixed, then this essentially is linear in and in. So we obtain some recurrent equation for a function, some function of t and n. No, it is more convenient to use number of steps and number of additional vertices, but they grow exactly the same. The main term is quite easy to calculate, and the main problem is to give an accurate estimate for the remainder term. To do this, we use this representation. So the main term t pd at x is in fact it cancels out. After that, we remain what one terms give values of determine the function pd, and what 1 over t is a remainder term. The remainder term, the recurrent equation gives such estimation of the remainder terms, and the accurate induction allows to prove that the remainder term bound is uniformly bounded with over all degrees. And the final step in the result is calculating the degree itself, the number of vertices over all possible values of n. That is a calculation of expectation over some function from a binomial distribution. It is easy to see that in fact the main term is just a value in a mean number of vertices. That is quite expected. And the remainder term is bounded by such a quantity. So it still is bounded by odd 1. That proves a theorem for the expectation. For the concentration, there can be several approaches to obtain the concentration. The simplest, the approach with minimal number of calculations is Azuma-Hefting inequality, but it gives a good bound only when d is quite small. When the expectation drops below a square root of number of edges, it is essentially useless. The main idea of our calculations is to estimate eventually the dispersion. To do this, estimate the expectation of square of number of vertices. It can be calculated using the same ideas. Unfortunately, the calculations are quite long, and I have not finished them yet. So only preliminary calculations show that this quantity is in fact the same, has the same order f as the expectation. So actually, if all my calculations are correct, then the concentration is true until this drops to O at 1. That is the first problem in degrees and out degrees.
I have
Any
a
questions?
question there. So I have a question there, which is when you normally we do Azuma Höftings because we sort of have many terms, and in order to be able to deal with it, we can only sum them up if you have this exponential decay. So if you do a second moment bound, that often doesn't give us good enough concentration. So why does it work here?
That is the rigorous equation Chebyshev's inequality. If sigma is any growing function, that this probability is tending to 0.
So I just wonder why people don't always do that. Just we normally don't do second moment bounds for this. We always do Höfting, you say, because we just don't think, or?
The significant disadvantage of that approach is a significant amount of calculations.
We often take the maximum of the least. That's the difference. So we want to show that this random variable n in d, e is uniformly close to its expectation. Uniformly indeed. And then the union bound is not going to give you good enough estimate.
Okay, now the second problem is to estimate number of edges between vertices of two given degrees. The motivation. We want to calculate the expected number of edges between two given vertices. But we do not know much about these vertices. We know only the in and out degrees. Thus, we also know from the previous part, from the previous problem, values, the expected and even with high probability number of total number of vertices with in degree D2 and out degree D1. So we can try to estimate the motivated quantity with the sum over all vertices of in degree D2 and out degree D1. And we define this quantity as the total number of edges with out degree of the source D1, one of parameters, and in degree of the target is D2, another parameters. The results, that the theorem. Well, no, there are many special cases. For common case, when every parameter is non-zero, it is proportional to number of vertices and to number of edges. And the coefficient of proportionality is sum of 8 quantities that can be calculated. That is the exact formula. They can be calculated using these exact formulas. The key component of the formulas is this double integral. The formal proof is the same, uses the same idea as the previous part. Just create a recurrent equation and accurately find the main term and accurately bound the remainder term. The recurrent equation gives some recurrent equations for the coefficient using values for these three pairs. And it turns out that this double integral satisfies to this equation with several variations. Variations are related to the fact that the recurrent equations for x t d1 d2 sometimes use one of terms in the recurrent equation uses the product of these two quantities, and these two quantities in fact have some structure that is different, that can be represented as sum of two terms. And of course, this double integral has a physical sense, otherwise it is quite hard to find this representation directly from the recurrent equation. And physical sense can be obtained from the fact that in this model can be the following quantity can be calculated. Given that we know in degree or correspondingly out degree in some time, we can estimate how the degree of the same vertex evolutes over time. This is not the rigor theorem, this is just motivation why this double integral has the sense to view, to consider. Accurate, this product of gamma functions is a coefficient before the double integral, and this is the quantity to be integrated. More strictly, the physical sense continued. The V and W represent two vertices between we calculate number of edges. And there are 8 cases according to whether the edge is oriented forward in the time or backward in the time. Whether the first vertex was created by new in adjoint process, and whether another vertex was created by one of these two processes. This takes h terms. Some of these have two terms inside the integral. If one for the created process also creates in an interesting edge, and one for a process when the interesting edge was generated later when the vertex is evolutes over time. Some of them have only other term. Also, this formula is not very useful as is, but it allows to calculate the asymptotic behavior of this quantity. In these formulas, A1 and 2 have EI constants depending on the only model parameters, and D1 and D2 grows. It is possible to, it is quite easy to calculate, to estimate this when D1 is very small compared to D2, and it can be noted that without the condition, this is just a product of two beta functions. So the same integral when D1 is very large compared to D2 can be calculated as the difference between product of beta functions and the estimation of asymptotic for swapped for this inequality in other way. Unfortunately, it is not so easy to calculate when D1 and D2 are of the same order. So I have not written the ready formulas yet, but they can be done. And the concentration, we do not use the approach with the second moment because this is absolutely a large amount of calculations. So we just use the Zuma-Höfting inequality, and it is easy to prove the concentration around a square root of number of edges multiplied by sum of degrees. Any questions about second part?
Question?
In fact, we already discussed this question, but maybe I ask again. So this is as simple as it gets, right? So you don't have any simpler expressions. So any simple asymptotics, even if they might be too rough. For degree-degree correlation, in particular, I'm interested for degree-degree kernel.
They can be done, but they are simple if one of degrees is significantly larger than the other. But I have not yet developed.
So for this particular model, you have not developed yet this.
The common formula. The special formulas, I have some special formulas. I just didn't write here. And if one of vertex is significantly larger, one of degrees is significantly larger than the other, that X just is asymptotically just product of D1 into the sum power by D2 to the other power. The powers depend on the model parameters, and also there is a quantity C in plus C out minus 2. If C in and C out are the same quantity as figure 8 in power law for distribution of the degrees. If their sum is less than 1, it is one situation. If the sum is greater than 1, this is another situation, and powers are slightly different.
Thank you.
It's the people, they calculated, they like to calculate these degree correlations in growing networks. It was studied about 12, 11 years for undirected networks. And there was a paper of Krapivsky and Riordan where they calculated it in very similar way, but for undirected networks. So also I could calculate it this way, more or less. And what is the principal difference? Because the formulas I see, they look, at least I remember asymptotic. Asymptotics are similar. And
Well,
principal difference from which is induced by directedness of the network.
well, there is the definition is slightly different. We consider respectively out degree and in degree instead the full degree.
they didn't take into they didn't take into account the new connections between already existing vertices. And what this produce some assertiveness or not. Can you say that this network is assortative or disassortative?
I'm not ready to answer this question. I have it. I don't remember the exact asymptotic, the exact asymptotic, and it is important. But I think it can be answered once the exact asymptotic is known.
Partially answering your question, because recently we also did, actually wrote a paper that where we analyzed with this relations and preferential attachment, and I will talk about it tomorrow. And we used your result, but the differences from what Evgeny is doing, or what you're doing, and what you did in your paper is that usually in your approach is like, okay, we write down the recursion, then we assume that in the asymptotic that we can take limits from both sides, and then we do the calculations. So this taking limits from both sides is a strong assumption, which not necessarily always true. And the difference from what Evgeny is doing here, or what from we were doing, is that we make these necessarily steps that justify this asymptotic transition. So once the transition is made, then all your calculations simply apply directly the way they are presented in your paper. And we didn't, to be honest, I did recompute it, but it was all correct. So, this step from recursions for given t to the asymptotic for infinite t, this is a strong transition which has to be justified, and this is the point, right?
Yes.
So did it help a little bit? I think the result is simply more detailed in what Evgeny is doing.
So actually, sort of on that question, do your formulas simplify if you assume there is no connections between old vertices? So if you put this parameter beta equals 0?
I do not think that this simplifies anything in this approach.
No, but your formulas look very complicated as we. So these, do they become easier if you?
Well, there is the answer, the exact answer, and it isn't quite simplifiable. I think that there are no simple formulas for the answer, so except asymptotic. There are no exact formulas for the answer that are significantly simpler than this. And anything that does not change the answer must operate either on the exact formulas or on the recurrent equation.
Okay, do we have more questions? No questions? Okay, good. We made up the 5 minutes we started late, so we, I think, switched to the thanks the speaker again. switch to our next speaker.
So you should stand up and introduce him.
Okay, our next speaker is Konstantin Avrachenkov from France, and I think he will talk about some semi-supervised learning methods.
Thank you. So also, first of all, I would like to say thank you to this wonderful workshop organizers. Everything runs smoothly, and the talks are very interesting, so it's really a pleasure to be here. Also, I would like to acknowledge my collaborators on this topic. So these are Marina Sokol, Alexei Mishenin, Paulo Gonçalves, and Arnaud Legoux. This presentation is based on a series of papers, not only on a single paper. I just do it like this, right? So just first a brief recap. The traditional classifiers work this way. We need to divide data in two sets, training set and classification set. And we train classifier on a training set and then apply to unclassified data. So this stage of training a classifier could be very demanding. In particular, if we have a lot of data and we need a work of live experts to perform classification. So then, motivated by these challenges, some researchers came up with an idea to actually train classifiers directly on a combination of raw data and training set. So we do have very few expert classifications, but in this approach, we really need really very few expert classifications. You'll see later how this works. So one of a large class of such semi-supervised learning algorithms are graph-based semi-supervised learning algorithms. And this type of algorithms are based on similarity graph. There are several ways to get such graph. One way is just by using radial basic function. So typically, a data point has a vector of attributes, which we can denote, say, by xi. So what we do, we, for example, take a norm between two data points, and then take an exponent with some weight. This method is called radial basis function method. So this way we have a graph, weighted graph. So each node in this graph corresponds to data points, and a weight on this graph corresponds to some degree of similarity between data points. However, in some applications, we even don't need to construct such a similarity graph. A graph is given to us. So take an example of Wikipedia. In Wikipedia, if two articles have links between them,
typically it indicates that they belong to the same topic. Or two, which I show later in more details, if two contents are downloaded by the same users, it often indicates that they represent the same interest group. So, okay, just to be a bit more formal, we want to classify data in K classes, and we have capital N data points. And suppose capital P data points are labeled. We denote by VK the set of label points. So small k runs from 1 to capital K. And we denote by capital D a diagonal matrix whose diagonal elements are equal just to the sums of the rows of the similarity matrix. So it's kind of generalization of degree matrix. So then for label points, we construct a labeling function, which we denote by y. Oh, sorry. By y. So y's are just vectors where we insert ones if we label that point. So these are basically indicator functions for the labeled points. We also have classification functions f. So each fk vector indicates in the ith position to which degree the ith element belongs to class K. So if fik element is significantly large, this means that the element I is very likely to belong to class K. Right. So the graph-based semi-supervised learning has two principal ideas. So the first principal idea is that the classification function should be made as close to labeling functions as possible. And the second idea is that these classification functions should change smoothly out the graph. So the values of the classification functions in two neighboring points in a graph should not differ much. And this, well, you can say kind of empirical observations or empirical suppositions could be expressed, for example, in the following optimization forms. So two probably the most well-known method in this framework are standard Laplacian-based method and normalized Laplacian-based method. So they are given by these optimization frameworks. And you see, so actually this optimization expresses a compromise trade-off between the smoothness of the classification function of the graph and its closeness to the labeling function. So this term, so if I and j are not neighbors, this is just 0 and we don't care. However, if I and j are neighbors, we see that we don't want this difference to be too large because we minimize, right? So this ensures that the classification function of two neighboring nodes, the values of the classification function of two neighboring nodes are close. On the other hand, we want that the classification function will be close to the labeling function. Okay, and here the optimization has a similar structure, but different weights. And mu is the regularization parameter. So what our first contribution is that we suggested a more unified framework, again, optimization framework. So we suggest an optimization framework where the weights depend on some parameter, sigma. So here now you have some dependence on sigma. And what is interesting, if sigma runs from 0 to 1, for certain values of sigma, like 1 or 1/2, we retrieve known classification schemes, like standard Laplacian or normalized Laplacian schemes. And for sigma, which is equal to 0, we actually obtain new interesting method, which we call PageRank-based method. So since it's a convex optimization, in fact, it's just a quadratic optimization, one either can use one of very efficient methods for solution of quadratic optimization, or one can even derive explicit formula for the stationary point, which is given here, and use some linear algebra method just to compute this formula.
Can you explain to us why it's called PageRank?
Yes, thank you. Actually, the next slide is convenient to explain why it's why we can call it PageRank-based method. So on this slide, we see these three important particular cases. So these are the first two cases are known methods, and sigma, when sigma is equal to 0, we obtain this expression, right? So now if we write the transpose expression, transpose stack A equals to mu plus mu. Sorry. So this is the transpose expression. And what is this? So it's degree, inverse degree matrix times weight matrix. So it's just the transition matrix, like in PageRank. So this is just alpha, like in PageRank, and y is just a kind of personalization vector. So you see it's like a personalized PageRank with y as a personalization vector, yes.
May I ask a question before I get lost completely? This f's, capital F's, they will be numbers between 0 and 1, or they will be only zeros and ones?
Actually, it doesn't matter. They could be, maybe it depends. I think they will be numbers between 0 and 1, but since it's classification function, you know, they don't have probabilistic interpretation. So what is important, their relative value, right? For which class they are larger or smaller. So we're going to compare elements of F. So F is look like this. I think it's very important to understand the structure. So say we have 4 classes, right? So then F has 4 columns, right? And if we look at row I, this element indicates the degree of belonging to a respective class. So we can perform classification by choosing element with the larger value of the classification function. So actually, the absolute value, we don't even care about absolute value. What is important for us is the relative difference in their values. I think because these series are positive, and y is positive, so they are not negative. So what is very helpful in the analysis of these methods, and of course also in the analysis of page rank, is a random walk interpretation. Jennifer told about this interpretation already this morning, but I remind this because my talk is also based on this, so it's important to understand this interpretation. So we consider random walk with absorption. So we say we start from some node, and with probability alpha, which is given by this quantity in our case, we make a move to a node uniformly chosen among our neighbors. And with probability 1 minus alpha, we just go into the absorbing state. So we do random walk with absorption. So then, if we start from node J, then this expression gives the personalized page rank relative to the seed node J. That was mentioned also in the morning talk by Jennifer. So what is interesting, we already can give the following nice interpretation of two limits in particular case of this semi-supervised learning. So when sigma is equal to 1, we have standard Laplacian method, and when sigma is equal to 0, we have a page rank-based method. So what first interpretation we can give? So suppose we have some label point for one class and label point for another class. And we have some point in question, say this. We want to find out if this point belongs to the class with circles or to a class with crosses. So what does standard Laplacian? We run a random walk on the similarity graph, and we run a random walk from node I. And we see how many times such a random walk visit one of the labeled points before absorption. So we count these numbers in expectation. And then we compare how many visits in expectation we have to these label points and to that label points. And to which label points we have smaller number of visits, to that class, we classify this point. So this is what is doing a standard Laplacian method. So what is doing page rank method? With a uniform distribution, we start from labeled points, and we do a random walk and count the number of visits to point I. And then we compare how many times we came to this point starting from this labeled point and starting from that labeled points. And from which set of labeled points we came more often to this class, we classify that point. So, and of course, they could give different classification, right? There's no reason why they should give always the same classification. So we obtained the following general result. how we decide which method classifies to which class which type of points. So the result goes like this. A data point I is classified by our generalized semi-supervised learning method into class K if the sum of products where dp is the degree of the label point p to the power sigma times qpi. And qpi is the probability of reaching node I before absorption if we start from the labeled point P. So there are some algebra, but actually the main ingredient of the proof is this decomposition result, which actually already turns out to be useful in many contexts. So before going a little bit in explaining various implications, and there are quite a number of conclusions we can draw from this result. Let me show you some example from a social network. So we consider as imaginary social network of characters from the Les Miserables novel of Victor Hugo. And actually, this network was collected by Donald Knuth. Various researchers, so general convention is that we have 6 major clusters. And let us look at the particular node which we call woman 2. So that's, yes? So it means if a character talks to another character. So if a character talks to one character, we give a directed link. So sometimes, you know, a character doesn't answer back. So then you have only one-way error. Okay, so we consider a very episodic character woman 2, which even doesn't have a name. And this episodic character, so I think I have a zoomed version, is connected to 3 clusters, to the clusters of Cosette, Valjean, and Javert. So, okay, if you don't mind, I propose we make a small social experiment. So, please, okay, first, let's forget about Javert. So, I give you a small hint that all semi-supervised methods classified either in Cosette cluster or in Valjean cluster. So we don't consider Javert cluster. Could you raise a hand if you think that the correct classification, or correct to your opinion, of course, don't worry, there's no correct or wrong answer. As we know, everything depends on the criteria, right? So according to your intuition, please raise a hand if you think that the correct classification is into Cosette cluster. And please hold it for a moment. So now, if you think that woman 2 should belong to Valjean cluster, could you please stand up and point to somebody who raised the hand, or point with your hand? So I just want to see, quickly, how many persons voted for each answer. So could you please, who decided that the correct answer is Cosette, raise the hand again? Yes. and who decides that the correct cluster is Valjean stands up and points to a person close. So I think it looks like we have more hands than standing persons. So Cosette cluster gain. Thank you very much for this little experiment. So what is good, I've given already 3 times this talk, and the result is consistent. So I'm very happy about this. So there should be something in this. And I'll tell you which semi-supervised learning works which way a bit later.
Did you try to change raising hands and standing person?
Yes, I also try to change every time. I use a bit different methodology for collecting statistics. So I think the experiment should be reasonably clean from social. Sorry?
I mean, now you started with Cosette, but you could also start with Valjean.
I think I also started at least once with Valjean. So they still was Cosette was obtained more votes than Valjean. Well, maybe people just like Cosette character more than Valjean. Okay. So let us see actually which semi-supervised learning classifies to which cluster. Okay, I think we can go. So what? Sorry, I first drink a little bit water. I used 20 minutes, right, so far, or a bit more. So let's see how this criteria works. So we have, suppose we're taking PageRank based method. So this means that we take sigma is equal to 0, and this factor doesn't play a role, right? So we need to compare only Qs. Again, what does Q mean? Q means the probability of reaching node I if we start from labeled points. So clearly, if we start from a node, and woman 2, by the way, just one hop away from both Cosette and Valjean node. So since Cosette has a smaller number of arcs, of course QPI is larger in this case, right? Because the probability of going somewhere else from Valjean is higher. So this is why in this particular example, if you take PageRank based method, it will classify the node woman 2 to Cosette cluster. So I think human brains is more accustomed with PageRank notion than standard Laplacian. Okay, so now let's see what happens in the case of standard Laplacian. In the case of standard Laplacian, we have sigma is equal to 1, but then we have a kind of uncertainty, right? Kind of uncertainty principle, like in physics. So on one hand, D, in the case of Valjean cluster, D is large, so we multiply by large D. On the other hand, we multiply by smaller q in the case of Valjean cluster. So this criteria cannot give us, well, a simple answer. So probably if you do computations, well, not probably because it's a theorem, so if you do computations, it will give you correct answer. But it's not easy to see it immediately. So let us, and what is nice, we can give an alternative formulation which can give us immediate answer, even without doing any computations. So for this, we need a very small Qt result. Actually, I'm pretty sure this result is known in one or another form somewhere else. So probably some of you can even point me to a literature. But at least in terms of page rank, I didn't see it before. So
Stationary distribution on a finite graph is 1 over the degree distribution.
no, it's a page rank, yes. It's a random walk with absorption.
Right, this is this matrix, Pij, I, Pi to J, and that's this PPRJI. Right? So what he's saying is that the ratio of the Pi to J to Pj to I is the ratio of degrees.
Yes.
And this I and J are not semi-connected, right?
No, any nodes. So this is the beauty of this result. So you take any graph. It's the only important condition is that the graph is undirected. So if the graph is directed, this result doesn't hold. So, So it means personalized page rank with the seed node I and the personalized page rank of node J.
It's what I was calling
I, in brackets.
Wait, but on one is I and Y, J. So the brackets is the
So inside the brackets is the seed, and this is just element, J element.
I is Pi to J in my notation.
Yeah. So look at this formula. So this is the personalization vector, which is EI. So 1 is just in the I position, and zeros everywhere. So we start from node I, and we see how often we come to node J. So actually, the proof is, just several lines. So how it goes, we just write what is personalized page rank, and we take D outside of these brackets of the inversion. And inside we have standard, modified standard Laplacian. So the key observation here is that for undirected graphs, the standard Laplacian is symmetric, and its inverse is also symmetric. So then what we do, we just take the jth element of this vector, and which is just this vector times vector Ej. And since this matrix is inverse, is symmetric, we can just swap I and J, right? So we put J here and I there, and that's it basically. Okay, so this little result. No, actually, I don't have intuition about this. So if somebody has not.
I mean, you would expect it to be, you would expect Pi to J to be proportional, to be scaling positively correlated.
Yes.
with the in degree of J, and similarly the other one, but then it's exactly that ratio, that that kind of all the differences in the
Yeah, all
intermediate
the,
stuff wash out. But I guess maybe that's just saying, I mean, maybe what you're saying is since it's an undirected graph, all the other stuff that can travel in both directions, and all that's left is the ratio of the degrees. I mean, I'm not saying that's a proof. I'm just saying in hindsight.
no, the proof is very simple. You see, the proof is simple. I don't have intuition. I don't have nice intuitive explanation of
But
this.
the intuitive
intonation.
explanation, I would say, is that you can't wipe out the difference in the in degree of I versus the in degree of J. Just you can't. But all the other stuff, everything travels in both directions along it because it's an undirected graph. So, I mean, only in infinite hindsight, with you telling me that this is true, do I come up with a hokey explanation, a hokey intuitive explanation of why it's true.
What if you use terminating random walk? Is it clear from that, maybe?
Sorry, use what?
The terminating random walk interpretation.
Because it's an undirected graph.
Maybe. I don't know.
So the personalized page rank I to J is that if you start
From I, yes.
and then
You count number of times you visit J. So this is somehow expected number of visits to J.
right,
But then,
No, absolutely.
so
yes, yes.
Yeah, yeah, it's time reversal. I mean, but.
Yes, should be related related also to time reversible.
And undirected graph, but still, you know,
what if you use the fact that you use another state as a terminating random walk? So I start with I, and I sort of terminate this probability. I mean, I do this, each step this probability.
By the way, it's not reversible. Page rank is not reversible.
no, page rank
It's not reversible.
But the terminating random walk is.
Yeah, but still, even in undirected case, for instance, the time to reach I from I, the time needed to reach J from I, and the time needed to reach I from J are not the same.
No.
So in this sense, because of starting in different points, you mess it up also. This sort of time restriction.
And of course, he has a very simple proof, so all of us are sitting here struggling to come up with.
Yes, I struggled to come up with not the proof interpretation. Why?
Exactly, that's all that's left. Exactly, it's reversible with respect to the degree, because everything can travel back and forth, except you can't compensate for the, you know, but it's only an infinite hindsight.
Okay.
That's nice. It's very nice.
So this little result allows us to come up with an alternative formulation. So what we do, we just plug in this result in our previous criterion to get a little bit different formulation like this. And now let's see how it works for our little social network graph. So now we consider we struggle to get interpretation for standard Laplacian, right? So in the case of standard Laplacian, sigma is equal to 1. If we plug here sigma is equal to 1, now in this interpretation, this part with degree disappears, right, which is nice. And we're left with just this personalized page rank, which allows very easy interpretation in our example. So now we start from not woman 2 and do personalized page rank to either Cosette or to Valjean. And of course, in this case, we visit much more often Valjean. Why? Because in one step we go either to Cosette or to Valjean, but then we stuck for a longer time at Valjean because this cluster is more untangled, right? Or just because it has larger degree and a random walk, it tends to return to it more often. So this alternative criterion helps us to give easy explanation, okay, for the other method. And another very nice interpretation is in terms of swaps introduced in the article by Anderson, Chun, and Lan. So what they introduced in that article is just for their local graph clustering, local graph cuts, is just the ratio page rank by the degree, right? So here I have,
Their backwards random walk, that's where the backwards
yeah.
random walk.
So here I have a little bit different, a little bit of generalization of this with 1 minus sigma. Okay. So actually, how 5 minutes, right? So I think that's interesting. So let's, I quickly go through formal interpretations of the first result. So what is very good, we're able to decouple the effect of sigma and alpha. So the effect of alpha, how often we restart our random walk, and sigma is just another parameter, right? And in our criteria, we completely decomposed these two effects. So sigma just in this factor of degree, and alpha is just inside personalized page rank. And we have complete decomposition. So then, when alpha goes to 1, Q also goes to 1 because, well, we come with probability 1 to not I. And we conclude that in this case, classes with the largest value of this sum attract all the points. And we see that the page rank case is again particular, because if we have the same number of label points in each class, we have a stability of classification. So all the other methods, they classify only all the points in one class. Only page rank method, independent of alpha, keeps some reasonable distribution of points among the classes. And it does this even in the unbalanced case. So we know that classification in the unbalanced case is very challenging. Right? So another interpretation is that page rank method typically takes from larger classes and gives to smaller classes, whereas standard Laplacian gives the opposite, makes the opposite. It takes from smaller classes and gives to larger ones. And we have one more very quite surprising conclusion. So if we take label points with the same degrees, it doesn't matter which semi-supervised learning method you take. They all work the same. So they all give the same results, which is not evident at all from the first sign. Okay, so let me just quickly give you some idea of some applications. So we analyzed some baby example where you can compute actually everything. So, well, you just can compute everything. We also checked clustered preferential attachment model, and it's confirmed all our observations, which I was discussing just before. So let me go to the two interesting applications. So first, the classification of Wikipedia article. We took 3 topics from Wikipedia: discrete mathematics, mathematical analysis, and applied mathematics, and classified articles according to experts' help and according to AMS mathematical topics classification. So we have a ground truth here. And then we applied our semi-supervised learning method. So the class is actually imbalanced. So you can see the distribution of nodes by the classes. And we have chosen just 5 label points for each class. So here what we have. And you can see that if we choose labeled points randomly from each class, somehow, indeed, the page rank method is the most stable method among all of semi-supervised learning methods. Okay, I also want to tell a couple of words about another very interesting application. We've done a classification of peer-to-peer traffic. So with the help of colleagues from another team from India, we're able to capture all BitTorrent, all peer-to-peer traffic in the internet. So really, everything that was downloading during 1 month in the world has been captured. Yeah, no. and I hope they don't approach me. So, how do we construct user graph? So if 2 users downloaded the same content, we had a link. And how we constructed content graph, if 1 user downloaded 2 different contents, we created a link between these 2 contents. Yes, so in 1 minute. So we classified by, for example, by languages and topics. And for instance, for the data sets of about 200 points corresponding to content classification. We've chosen just 50 label points for each language and obtained 95% of accuracy. So we also done some classification, so, well, it also works well for content classification. I stop here, and if you have any questions, I will be glad to answer.
Yeah. So I think since we're running late, we'll
we can take
ask
also.
the question at coffee.
Yes,
And we
of
come
course.
back at 20 past.
Thank you.
It's really pretty. It's really nice. Well, it's nice that you see this. No, it's really nice.
It has a nice